Welcome back, everyone. We just learned about the theory behind gradient boosting. Let's go ahead and revisit that mushroom dataset, and let's code through a walkthrough of gradient boosting. Not really going to do any exploratory data analysis since we're already familiar with the data. Instead, now we're going to focus on applying a grid search to the boosting methods. Keep in mind, you can also do a grid search with the add-a-boost to figure out best number of estimators. Last time we just plotted it out. Let's put all these ideas together in the notebook. I'll see you there. Okay, here I am at the notebook, imported NumPy, Pandas, Matplotlib.pyplot, and Seaborn. Let's read in that same mushroom data set as we had before. We'll say pd read CSV, and then I'm going to say data, and then it's the mushrooms.csv file, just a tab autocomplete there. And it's the same data frame we worked with last time. Let's go ahead and do the train test split as well as data preparation for the dummy variables. So we will separate out the features by saying dx is equal to 𝑑f_drop_class, just as we did before, along axes is equal to 1. Then I'm going to say x is equal to pd get dummies on x, and then say drop first is equal to true. And then we'll say y is equal to df class. All right, so now let's go ahead and do our train test split. We'll say from scikit-learn model selection import train test split. After that, we'll say train test split, do shift tab here in order to actually find the tuple unpacking code. So we're just going to grab this, scroll down until you find it. Should be right here. Copy and paste that in. And keep in mind, since we're doing a grid search, this test set is technically going to act like a holdout test set. So you probably want to make your test size a little smaller than 30%. Maybe just hold out 10% as your final performance data set, or 15, depending on how large your data set is. We can do 0.1 or 0.15. That should be about right. Want to make it a little smaller since, again, we're doing cross-validation on the full training set. And once we've done that, we can go ahead and move on to gradient boosting and the grid search. For that, we can say from scikit-learn .ensemble, and we import, and depending on what kind of task you're doing, you import gradient boosting classifier or regressor. We're doing classification task, poisonous or edible. And something I keep mentioning throughout this lecture series is that the boosting methods are technically meta-learning algorithms, where you can pass in any other machine learning algorithm, but they tend to perform best with decision tree based methods. And it's so expected that you use decision trees with these boosting methods that if you take a look at the documentation, scikit-learn ensemble gradient boosting classifier, it will actually just set everything up for a decision tree. So it works best with decision trees, and in fact you can see all the parameters you can set for the decision trees themselves. And notice that the max depth is now greater than just 1. Previously, with add-a-boost, your max depth would have been 1 because you just wanted stumps. And gradient boosting classifier, what the learning process works best with is if you allow these trees to grow. And of course, this is something you can perform a grid search for. Max depth of 3 or 4, as well as the right number of estimators, as well as the learning rate. So lots of different things you can experiment with, which is why you really should be using a grid search for gradient boosting classifier. And really, any robust model where there's a search for the best hyperparameters is a good case for a grid search with cross-validation. So let's come back down here and set up our grid search. We'll say from scikit-learn model selection import grid search CV. And then we're going to have a parameter grid, and we can set up number of estimators as something to explore. Not a big deal to have a lot of estimators here, so I can do something like 50 versus 100. I can also experiment with my learning rate. So we saw learning rate. If we go back to make sure we're passing this in correctly, it's learning underscore rate. Recall these keys should match up. The default is 0.1, so maybe we explore something kind of half as fast as that, 0.05, or something much faster, like twice that, 0.2. And then we can also check out the max depth of the trees. These are kind of the critical ones you want to be experimenting with. Default is 3, so we can explore something like 3, 4, and 5. Okay, obviously the more features you have, the more you want to experiment with for things like max depth and leaves, etc. So we're ready to go here. Let's set up our model. We'll say GB model for gradient boosting model is equal to the default gradient boosting classifier. And then I will say my grid is equal to a grid search CV, where I pass in my base model, GB model, with my parameter grid that I'm going to explore. Run that, and let's fit this to our training data. We say fit xtrain, ytrain, and it's going to fit with cross-validation and essentially check out which of those parameters is the best performing. Obviously, the more parameters you test for, the longer this fit is going to take. And I didn't check off verbose equal to 1 or 2 because I'm going to just fast forward in time until this is done training. All right, so that's finished now training. I fast forward in time a little bit. It took about a minute on my computer, and it may take longer or quicker on your computer depending on your RAM and what's available to you. What we're going to do now is check out the performance. We'll say from scikit-learn.metrics import, and we can import our classification report as well as things like plot confusion matrix or accuracy score. Lots of different things we can do here. Let's plot confusion matrix, and let's also get the accuracy score. So I'm just doing tab to autocomplete these, but classification report, plot confusion matrix, and accuracy score. Go ahead and run those, and then we're going to say is predictions is equal to grid.predict of x test. And if you check out your predictions, they should just be a bunch of P's and E's for poisonous versus edible. Now you're probably wondering, what parameters did the grid actually choose? Well, you can get those by saying grid and then call for the best estimator, because that's what the estimator ends up using. And you'll notice that it just says estimator is gradient boosted classifier, doesn't give you any details there. So instead, we can also search for is best params in order to get the full details, where learning rate was 0.1, max depth of 3, and estimators as 100. And if you check out the documentation, those are actually the default values. So even with a grid search, notice we use the default learning rate, the default max depth, and the default number of estimators. So these are actually really well chosen defaults, because even in exploring other values in our grid search, those ended up being the best, which is why when you see best estimator reported back, it actually didn't show you anything because these are all default values. Okay, so we know gradient boosted classifier, the default values were the best for this particular performance metric, and let's check out the accuracy then. So what I'm going to go ahead and do is print out the classification report. I'm going to say classification report, and I'm going to pass in y-test versus my predictions here. So my predictions, run that, and we can see, boom, we actually performed perfect. Now keep in mind, if you used a different split or a different randomization in your random state, this is going to be slightly different, or if you chose a different size, but this is absolutely fantastic performance. Obviously, you want to be skeptical a little bit when you see something performing this well, but given what we saw before, it's not too crazy that we're getting perfect performance on just the test set, especially if you compare this to what we saw in AdaBoost on the same test set. Even with just one stump, you were performing already pretty well. So what about feature importances? We decided earlier that we also wanted to try to get a set of guidelines on what features were important. So for that, you're going to end up calling grid, then call best estimator, and then off of this, you can call things like feature importances. So keep that in mind. If you're ever running a grid search and you want to look at your model, and if you go down here in the documentation, the attributes of your model are all available here. What you should know is those are not going to be available directly off the grid. Instead, they're available directly off your best estimator. So we have feature importances here, and it's an array of values on how important each feature is. Notice some of these numbers are absolutely tiny. So you see 1.7 times 10 to the negative 16. So they're essentially almost zeros for a lot of these. Let's set up a data frame to try to plot this out. I'm going to say the following, that feature import is equal to this right here, grid best estimator feature importances. Run that, and let's set up a important features data frame, just as we did in the previous lectures. We'll say PD data frame index is equal to x.columns, and then the data is equal to this feature importance, and then the columns is equal to, let's just label it importance. There we go. And if I check out now the importance of my features, I have this nice feature name and then the importance of what the model thinks. So notice some of them it's 0, and just because of the way floating numbers work on a computer, for some of them, even though it kind of wants to say 0, it'll just put an absolutely tiny number, which essentially acts as 0. And again, these are not the learning rates, or it's not some sort of alpha coefficient. It's just based off the model and what it chose to split on all these decision trees, which features are giving you a lot of data that is based off that Gini impurity value. And so something we can do here is plot out these values, probably don't want to plot out all these features that are close to 0. So instead, let's say important features. We're going to say important features here, and let's just grab where import feature importance, so to speak, where the importance is at least, let's say, greater than 0.005 or something like that. We'll say 0.00, let's say 0005. Just kind of choose a really small number, essentially just to get rid of all these numbers that are very close to 0. So give some sort of minimum threshold that they have to beat there. And there we can see, here are some values that we can actually plot out. That way we don't have just a bunch of things that look like 0 in our plot. So to do that, we can use just a simple seaborn bar plot. I can say sns.barplot, and then pass in the important features series as my data. And then what I want along the x are the actual important features. The names, recall that's the index. And then what I can do here is for y, just have that be equal to the name importance. Make sure we have an equal sign there. And if you just run this by itself, you'll notice you'll get a smaller plot, and you'll also notice that things are not in order. So let's go ahead and edit this a little bit. What I'm going to do is I'm going to redefine important features as its sorted version. So I'm going to say important features is equal to important features. And then I'm going to sort values based off importance. There we go. So go ahead and run that. And then when you run that again, you should see now everything is in order. However, we're still not really good on size or the rotation of the x ticks. So let's just quickly add that in as well. We'll say plt x ticks and say rotation is equal to 90 degrees. Go ahead and rotate that, put a semicolon so you don't see a bunch of text output. And then finally, let's make this figure a little sharper and a little larger. We can say something like fig size is equal to 12:8 with a higher DPI. Then we run that, and there we go. Now we have a nice looking plot that we can check out. And notice now for gradient boosting, just as we saw earlier when we were dealing with adaptive boosting with one single stump, it looks like having no odor is now a very important feature, and it's quite more important than any other feature. So again, if we were developing guidelines, telling people to check, does this mushroom have an odor or not, would be a very good guideline to just set there without having to check a multitude of features, even though obviously our gradient boosting model can check more than just one single feature. Okay, that's it. I'll see you at the next lecture.